In this podcast, we're going to talk about what a cyclic hemiacetal is, how it's formed, and why you should care. All right, so let's start by going back and remembering what an acetal versus a hemiacetal is. So we will focus on a carbon. It could be at the end of a chain. It could be in the middle of a chain. A hemiacetal is a carbon with an OR group and an OH group coming off of the same carbon. And an acetal has two OR groups coming off of the same carbon. So that's just a reminder of what those are. In a cyclic hemiacetal, you have a reaction of a compound that has an aldehyde or ketone, and it will react with a hydroxyl group or an OH group on the same molecule. So you have at two ends an aldehyde or ketone and a hydroxyl, and those are going to come together, react to form a cyclic structure. They can contain 5 or 6-membered rings, and I have an example down here of a 5-membered ring and a 6-membered ring. And the cyclic form is more stable than the acyclic form, which is why it tends to do this. So if you have an aldehyde or ketone and a hydroxyl group on the same molecule, most likely that's not as stable as the cyclic form, which is why the reaction happens. And just to help you kind of identify that this is a cyclic hemiacetal, we have a carbon. And this carbon has an OH group and it has an O, and we would consider all this junk an OR group. So this would be considered a hemiacetal. Same thing here. We have a carbon that has both an OH group coming off of it and an OR group coming off of it. So that's how we would identify cyclic hemiacetals. So let's talk specifically about these guys, how these guys form. Here we have 5-hydroxypentanal. So it has an aldehyde and it has an OH group. Essentially, this alcohol group, this hydroxyl group, is going to come around and is going to attack the carbonyl. So just to give you an idea of what this looks like, I'm going to have this wrap around on itself. Okay, so here's carbon 1, 2, 3, 4, 5. All right, so this is carbon 1, 2, 3, 4, 5. Okay, and on here we have our OH group. So the OH is going to attack. And what that's going to do is it's going to form this cyclic structure. So here's our acetal. This is where our acetal is forming. We form a cyclic hemiacetal. Now, we're in Intro to Organic and Biochemistry. This is not something that you have to know exactly how this forms, but it is important to understand that this is similar to how you would form an acyclic hemiacetal. You're going to have this hydroxyl acting as your alcohol, and you're going to have a carbonyl, and it may be an aldehyde at the end of the chain, or it may be a ketone. Either way, it doesn't matter. It reacts with itself, forming this ring structure that contains a hemiacetal in it. All right, so why should you care about cyclic hemiacetals? Cyclic hemiacetals are vitally important in life. Glucose is a great example of a cyclic hemiacetal. Carbohydrates are full of cyclic hemiacetals, whether they are polysaccharides or monosaccharides or disaccharides, they're all full of these cyclic hemiacetals. Just to give you an example, because it is a little hard to visualize these guys at first, look for this is your OR group right here. So imagine this as being O attached to this whole ring. Right here is our carbon. It's attached to an OR group and it's also attached to a hydroxyl. So that's where our cyclic hemiacetal is. And as we go through our carbohydrate chapter, we'll talk a lot more about cyclic hemiacetals, and we'll work on also identifying them in larger structures as well. All right, since first recording this, I decided I wanted to include a couple health notes and a couple ways that you would see cyclic hemiacetals in questions on exams. So here we see digoxin, which we are going to talk about in a couple slides. So it's a very complex molecule, and something you'd be asked to do is to identify all of the cyclic acetals or hemiacetals that you might see. So your book has already done this for us, but I want to talk to you about how to find those. So we are always looking for oxygens. So these oxygens are in red right here. We want to look at the carbon that's in between those oxygens, because we know that we could have an OR or an OH group coming off of both of those, and that's going to determine whether it's a hemiacetal or a full acetal, hemiketal, ketal. So What's tough about these cyclic structures is we know that this carbon is attached to 1, 2, 3 other molecules. What is not shown in the cyclic structure is the hydrogen that's included as well. Because that center carbon right here has a hydrogen that it's attached to, that means it was at one time an aldehyde. Okay, so this would be an acetal. And we would consider everything that this is attached to as being an R group, and everything that this is attached to as being another R group. So this carbon in the center that we've highlighted in yellow is attached to 2 OR groups, which is what makes it that acetal. Looking at this next acetal, so we see our oxygens. We're going to look right between them here for our carbon. This carbon is attached to 1, 2, 3 others, so we can assume there's an H. Because there's an H on the center carbon, it has to be an acetal. Is it a hemiacetal or is it a full acetal? For that, we look to what's bonded to the oxygen groups. Here we have anything other than a hydrogen. Here we have anything other than a hydrogen, so it has to be an R group. We have 2 OR groups, therefore it's an acetal. What I want you to caution you about and for you to be careful of is seeing something like this oxygen and this OH group. That can be misleading. We actually have 2 carbons in between there. They're not coming off of the same carbon, so therefore you don't have a situation where you could have an acetal or hemiacetal. So on the previous slide, we saw digoxin, and I said I wasn't even going to talk about it yet, but here we are, now we're talking about it. Woolly foxglove is this plant that you're seeing here, and it is the source of the heart drug digoxin, and this is what we looked at as a molecule on the last slide. And digoxin has been found to be a useful medicine in the treatment of congestive heart failure and other heart ailments, so it's a pretty medically important molecule with its acetals in it. Another example of cyclic acetals and hemiacetals can be found in the disaccharide lactose. Lactose is a carbohydrate found in milk, and it's the combination of 2 monosaccharides, and it has 1 acetal and 1 hemiacetal. So here we see our oxygens that we always look out for, and there's the carbon in between them. These are OR groups on each side. And we know that we're missing, not shown in the skeletal structure, is that hydrogen coming off of the center carbon. So these are acetals. Down lower, we see a good example of a hemiacetal. So this oxygen is attached to anything besides a hydrogen. So this is our OR group. And the second oxygen has a hydrogen on it, which makes it a hemiacetal because this carbon was at the end of a chain. Lactose is kind of a fun sugar because not everybody is able to take that disaccharide and break it into its monosaccharides and break it down for energy. If you are lactose intolerant, you are not able to split apart this disaccharide into its monosaccharides because you do not have the enzyme lactase, which is needed to digest and absorb lactose. So if you are lactose intolerant and you drink milk, or anything with lactose in it, you are probably going to have some pretty severe abdominal cramping and recurrent diarrhea. It's a good thing to avoid. All right, so as we discussed at the beginning of the podcast, we talked about the plant defense mechanism, the toxin solanin. This is in the plants that are in the Solanaceae family, so think about tomatoes, potatoes, ground cherries, that family. They're all going to produce certain levels of solanin. Solanin is that complex molecule with 3 acetals in it. We haven't shown it, doesn't matter, you don't have to memorize the molecule. Let's talk about that though, because I eat a ton of potatoes. So what is my risk for solanin toxicity? So for your average adult, it's going to take anywhere between 200 to 400 milligrams of solanin to be toxic. That doesn't seem like a lot, okay? That's like 2 to 4 grams. It's not very much. So the question then becomes, well, how many milligrams of solanin is in your typical potato? There is 0.2 milligrams per single potato, oh, I smell a unit conversion coming, is about 0.2 milligrams per potato. So let's just say, you know, things are on the light end and 200 milligrams will take you out. Okay, if every potato, and this is not a green potato, has 0.2 milligrams. Obviously, the greener the potato is going to get, the more solanine you're going to have, the less potatoes it would take to kill you. Okay, so it's just a simple unit conversion, 200 milligrams to kill you. One potato has 0.2 milligrams. We are looking at about 1,000 potatoes you would have to eat in order to kill the average person. Nobody's going to do that. It's not a good way to kill people. And who would have thought you'd be sitting at home listening to this lecture while we calculated how many potatoes you need to eat to die? Funny how life is.